Complexity. You may have an intuitive understanding of what complexity means, but how does it differ from something that's just plain complicated? And why does it matter? In other words, what makes something a complex system? Systems thinking is particularly useful when dealing with complexity. Plenty of problems are complicated or hard to solve, but complexity is something different, and understanding it can help us figure out why cancer is so hard to treat. Let's turn to an example where modeling a complex system has already made a huge difference to humankind. Hurricanes. Weather modeling has been somewhat of a success story for systems thinking, and can give us an idea as to what success might look like for systems biology and cancer. To understand the difference between complicated problems and complexity, imagine a fan blowing in an office. This is a simple scenario, and it would be easy to understand how the fan will affect other things in the room. For example, a pencil on the desk might roll off due to the wind, and it will fall on the floor. Importantly, we can predict what happens based solely on the underlying principles of physics. We can intuitively understand where the pencil would end up without needing to go buy a fan and check for ourselves. This is a complicated rather than complex problem. How do we go from this simple system to understanding and predicting the movement of a hurricane? Imagine now that I could give you information on the prevailing weather conditions, like temperature, humidity, or large-scale wind patterns. With this information, could you predict where a hurricane would form? While you might have some ideas based on patterns of past hurricane formation, it would be difficult to use intuition alone to find an answer. By the way, there's a hurricane forming here. The answer is surprisingly difficult because hurricanes arise in the complex system of weather. Complex systems contain several simple components, like air molecules, that interact in nonlinear ways to produce unexpected behaviors or emergent behaviors. These are patterns that the whole exhibits but individual parts lack, and hurricanes are one such example. Importantly, it is not possible to calculate where a hurricane emerges or ends up solely using equations from physics, the way we could for a pencil rolling off a desk. To predict the formation of a hurricane, the event must be simulated. We must make a model that matches reality as closely as possible, and then watch as the model evolves. Through systems modeling of the weather, we are better able to predict what the course of a hurricane will be. For example, in 2005, Hurricane Katrina devastated the southern United States, particularly New Orleans, in part due to high uncertainty in the predicted track of the hurricane. Only 10 years later, weather modeling improved enough to reduce the margin of error in the prediction by 40%. And today, forecasting models are even better. In this case, better modeling leads to better predictions and can save lives. Just like hurricane modeling, modeling cancer as a complex system can help save lives. Cancer is a complex system because a relatively simple event, a mutation, leads to individual components, the mutated cells, that can interact in non-intuitive ways. These interactions give rise to unexpected emergent behaviors such as metastasis, heterogeneous phenotypes, and therapy resistance. Just like weather systems, where complexity exists at a local and global scale, it's important to think about complexity in cancer on multiple levels, from genes to patients. Let's consider how some of these components interact. At the molecular level, components might be proteins in a signaling cascade.
These cells are driven by numerous pathways that are typically cascades where lots of proteins are talking to each other.
So many things out there that cells could respond to. There's so much internal machinery of the way that they could transduce that information.
We attempt to try to understand what all of those molecules are doing and to try to understand how all of those pieces actually connect together in order to make a decision.
And so understanding those processes, how those cancer cells take those substrates, those resources from the environment is very complex, and we need computer models to try to understand those processes.
At the cellular level, different cell types interact and can cause drastic phenotype changes.
We're interested in the biochemistry of how cancer cells make decisions. For example, how a cancer cell decides should it die or not in response to chemotherapy or targeted therapy.
There's also in a cancer like glioblastoma incredible heterogeneity, and so it's not sort of monolithic where it's like one mutation drives it. There's just too much happening. I've heard it described as like whack-a-mole, for example. Sort of you smack one target and two other drivers of the cancer can pop up to compensate.
Hopefully you are already getting a sense of why systems biologists believe modeling cancer as a complex system is needed to make sense of this disease. Therapies today often don't help everyone, or they lead to relapse because they treat cancer like a complicated problem rather than a complex one. Modeling complexity at every scale can help us predict when certain patterns occur and how to prevent them, leading to lives saved.